Okay, this are some of the notes for lesson 7.8. This is graphing radical equations or graphing radical functions. Alright, so I've got my graph paper set up, and well, let's look at two of these things first by looking at the function x squared. Now, we should know by now that's a parabola. It's got its vertex at the origin, and we can find some values for this, like 1 gives us 1 and 2 gives us 4. And we've also learned that there's an axis of symmetry running straight through that vertex, and that those 2 points we just graphed have reflections about that line. So there's our parabola. Okay. Now the inverse of this would be plus or minus the square root of x, and so that looks as follows. Okay, it just, remember, exchanges x and y values. I did notice on some of your graphs you weren't having much of a curved shape to your parabolas. And so they do have that nice gentle curve. Okay, and we can see that also in the radical function. Now the radical equation. Now you can see this blue one is not a function. Okay. Well, in the radical functions, because we are graphing functions, what we do is we only look at one half of this thing. So you're going to be graphing either the y equals root x as a function, or you'll be graphing the y equals negative root x. Okay. And so if it were the root x part of it, just the positive root x, you'd get the top half. And if you get the negative root x part of it, you would end up with the bottom half of it. But you're going to have either one or the other. Notice in our original function f of x equals x squared, that thing does not give us an inverse function. However, we spoke about domain and range today in the class and how we calculate those. We can force a different domain on our original function. In this case, the original domain was for f of x equals x squared. It had the domain of all real numbers. However, if instead of doing that we say, okay, for the original function, let's take our domain and let's just limit it to x's that are greater than or equal to 0, what would that cause it to happen is it would eliminate this side, and it would just give us that side. And so all of our quadratics that don't have inverses, turns out they do have inverses, or inverse functions rather, if we limit domain. And again, here's that line, y equals x, and you can see those two are perfectly mirror images. They both pass the vertical line test, so they're functions. Okay, that's a lot of the details. For right now, though, we just need to focus on, can we graph these radical functions? So on the next slide, what we're going to do is we're going to graph this function again, y equals root x, and we'll look at how to graph that very quickly. We kind of have a sense of what it's going to look like, and you just generate points. 0 gives us 0, 1 gives us 1. You don't want to do 2, because 2 gives us root 2. And I don't know what root 2 is, 1.4 or something. And instead, what we're going to do is jump to a 4, because the square root of 4 we can do. So it's very easy, and we're only doing positive root 2. There's 1 gives us 1, and here's 4 gives us 2. The next good number to do is not 25, next one is 9, but we don't want to go all the way to 9, so our graph doesn't allow it. So that's what it looks like. Now, we're going to use a method that we used in previous sections to graph variations on this function. In the first type, let's call it g of x, is what happens if we add something to our function. Plus, let's say 3. Well, what it would do to our list here, for our y values, the outputs, it would just add 3 to every single one of these. But we don't want to have to do, okay, 0 gives me 3, etc. What we do is we notice it just bumps up where it starts by 3 units. So it's going to start up here at 0, 3. And then we use that point as a new axis, so to speak. All we're doing is shifting where we're counting from. And we use exactly the same points when we count from that position. So 0, 0 is the point we already have graphed. Then 1, 1, and then we count out 1, 2, 3, 4 on this new axis. We go up 2, and there's another point. And so we get the exact same graph as we had in green there, but it's now bumped up by 3 units. We've translated it vertically by 3 points. We can do the same thing if we want to go downward. Let's grab red here. Let's call it h of x. Let's say we want to go down by 4 units. That's fine. We drop down by 4 units. 1 gives us 1, and 4 gives us, there's 4 units from our new vertex or beginning point, and it's that one right there. So we can graph these just if we know what root x looks like. Of course, we don't always just shift these equations up or down. Sometimes we shift them left and right. So here's the standard parent function. 4 gives us 2 right there. And now let's make g of x, and let's take something away from the inside. Say x minus 2. Now if we think about the function in red that we have, x and y, and 0 gave us 0, and 1 gave us 1, and 4 rather, gave us 2. What this function does is, when you plug in a 0, it actually subtracts 2 from it. When you plug in a 1, it subtracts 2. When you plug in a 4, it subtracts 2. So what it does is, you plug in an x value like 0, but it acts like, it doesn't act like 0 acts until you actually put a 2 into that function. Once you put a 2 into that function for x, you'll notice you get 0. So the positive 2 acts like a 0, a positive 3 acts like a 1, because 3 minus 2 is 1, and a 6 acts like a 4. The way we always talked about it in previous discussions of translations is to figure out how much this thing shifts you, and whether it shifts you left or right, is determine what the value that makes, what value for x makes this stuff equal 0. In this case, the answer is 2. So that 2 shifts it to the right, and then we follow the same pattern, 1, 1, and 4, 2. So it'll look like that. We can shift it to the left by adding something. Now negative 4 makes it act like 0, so we plug in a negative 4, and out comes a 0, and then it counts exactly the same way using that new point as our origin. So there's 1, 2, 3, 4, and then up 2. So there is f of x, this is g of x, and this is h of x. Of course, we can do these things in combinations. Here's f of x again, root x, 0, 0, 1, 1, 4, 2, just like that. And now let's shift it to the right by 2, and let's shift it up by 3. Okay, so the 2 for an x value makes it 0, so that's a shift of right by 2. And the 3 makes it go up by 3. 1, 2, 3. And so the vertex, or the starting point for this, will be right up there at 2, 3. And then it acts just like the other function, 1, 1, and 4. 1, 2, 3, 4, 2. Now, let's do one more thing to this. Let's see what happens if we put a negative sign out in front of it. Okay. What this is going to do is calculate the starting point again, but then we're going to take the opposite of that. Again, well, let's look at it for the original function first. F of x equals negative root x. You can see what it's going to do. It's going to take 0, give you 0, and it's going to take, let's find a decent color. There we go. It's going to take 1 and give you a negative 1, and take 4 and give you a negative 2. So remember, that was that bottom half of the parabola that we didn't have to graph because we were only doing the positive part. And so for this blue one, if we put a negative sign out in front of that, guess what it gives us? It flips the whole thing over, and we have the bottom half. Now you wouldn't graph both the top and the bottom half. If the problem had a negative, you'd be graphing the bottom half. If the problem had a positive, you'd graph the one in blue. Let's do another one of those. Let's say we've got f of x equals negative root x plus 3 minus 4. Our shift is 3 to the left and down 4. Right there. This is going to be the bottom half because of that negative sign. It's going to be 1, 1, and 1, 2, 3, 4, down 2. Right there. We put, how about, let's do 9. We can go 9 steps. 1, 2, 9 gives you 3. Remember, our base function is root x, so the square root of 9 equals 3. So if we go 9 steps, 1, 2, 5, 6, 7, 8, 9, we go down 1, 2, 3. So it goes through that point. And there's that one. So this is what we know so far. We can take a radical function. We see how it looks like this half of parabola laying on its side. We've seen how we can shift that half of parabola up and to the right, or down and to the left, or just right, or just up, or just down. And we've seen how we can take them and get them to turn upside down and move around. So we can graph a bunch of those things. What we haven't shown yet is how do we get these things to face the other direction in this fashion, and of course move them around. Well, to do that, we're going to put the negative sign in front of the x under the radical. Watch what happens now. When I plug in 0, out comes 0. I get opposite of 0, which is 0. Square root of 0 is 0. If I plug in 1, I get the square root of negative 1. I can't do that. I can't plug in 4. I get the square root of negative 4. I can't do that. In fact, what I have to do is plug in negative x values. Negative 1, because of the negative sign in front, becomes positive 1. And when I plug in negative 4, I get the square root of positive 4, which is 2. So if I wanted to graph that function, let me erase these quickly, I would say, alright, instead of going 1, 1, you're going to go negative 1, 1, and you go negative 4, 2. And so we've now flipped them to point in the negative x direction. Once we recognize that's what's happening, we can graph any of these things very quickly. Let's look at this function. So I'm going to use function notation. Equal to negative of negative x plus 2 plus 3. This is about as hard as they get. What we notice in here, first of all, is that a negative 2 makes that positive. Because we have negative, oops, not negative 2. Positive 2 makes that positive, or equal 0. And this is going to shift it up by 3. So this is going to be a shift of right by 2. And a shift up of 3. So our new starting point is right there. It is going to point to the left because of the negative x inside, and it's going to be upside down because of the negative on the outside. So it's going to go 1, 1, upside down, so it's 1, negative 1. It's going to go 4 and down 2, like so. Okay, I hope that helps you with your homework.